Professor Dipankar Banerjee currently serves as the Vice-Chancellor of the Indian Institute of Space, Science and Technology, IIST, in Thiruvananthapuram, and previously held the position of Director at Aryabhatta Research Institute of Observational Science in Nainital. As an astrophysicist, he holds a bachelor degree in physics from St. Xavier's College and master degree in theoretical physics from University of Kolkata. His doctoral research was conducted at Indian Institute of Astrophysics. He completed two postdoctoral tenure at esteemed institutions in Europe. Prior to his current role, he was a senior professor at Indian Institute of Astrophysics. Professor Banerjee is the co-chair of Science Working Group for the Aditya L1 mission. Aditya L1 is the India's inaugural dedicated mission to study the sun, launched by Indian Space Research Organization ISRO on September 2, 2023. He is also actively involved in NASA's Punch mission. Additionally, he is a fellow of Indian Academy of Sciences, the National Science Academy, the Royal Astronomical Society, and serve as immediate past president of Astronomical Society of India. So without a further delay, I would like to invite Professor Dipankar Banerjee to please deliver his lecture.
Thank you very much for this opportunity. I know we are heading into the lunch break, and probably this is the last talk in this series. So I will try to keep it brief and will be happy to answer the questions what you may have. So this first slide gives you an impression that we are here in the Earth, and we are protected from the radiation and the particles which are coming from the sun by virtue of its own magnetic field. And what you see here is this magnetic field structure of Earth, and that has enabled our life on Earth as well. This is a very, very important element. There are, certain cartoons which is drawn inside the sun from observations. We have reasonable good knowledge about what is happening inside the sun. But today I will be primarily talking about certain features which you see on the solar surface and the atmosphere of the sun, and certain activities or big explosions which happens in the form of solar storms. And when such solar storms happen, here is a picture which is shown. They travel through the interplanetary space all the way to the Earth, and it interacts with Earth atmosphere. And since today we are, in the realm of, the space, era, there we have so many assets in space, which is beyond our magnetic shield, which is here. And there are also possibilities of now human space flight program making colonies in moon. So we need to protect these, assets and humans in space. For that, we need to understand when such solar storms can happen and why such solar storms have happened and so on. So that's my subject of today's discussion. So sun is a best studied example because it is our nearest star. So we do have a good amount of knowledge about solar interior as well, where this thermonuclear reaction takes place, and then the energy is there, and the sun or any star is having all this energy because of this nuclear reaction which happens in the interior. But today I'm not going to talk much about the interior, but then this is a picture of the solar atmosphere taken from one of the NASA satellites. You see that there are regions on the sun in the atmosphere which are brighter than the surrounding. And these features or these regions, we call them active region, they evolve, with time, and they make a lot of, dynamic, activities as well. Of course, you do any science, you need to go back to history of science. And as you can see, that we need to actually appreciate what our ancestors have done. And in modern science, this is the, I would say, birth of modern science after the discovery of the telescopes. And Galileo Galilei, this is a gentleman, he made a phenomenal change in our understanding of the universe per se. He was also a person who looked at the sun. So he used this newly invented telescopes, and what is shown here in the right, animation is his hand drawing. So what he observed is that on the solar surface there are these dark regions, which we call now as sunspots, and we now also know that these are regions where there is a presence of strong magnetic field. 400 years back, Galileo didn't know about it. Magnetic field was not discovered until, little more than 100 years. So, but he still observed that these, features are moving to the subsequent days, and that allowed him to even say that sun is rotating about its own axis, because this is actually solar north. This is the east-west direction, and you could see that sunspot today is there, and the next day it is to the right, and then subsequently to the right, and so on. That is only possible if these sun is rotating about its own object. So sun rotates about its own axis was also pointed out by Galileo, and these are the hand drawing from Galileo, which allows us to really find the behavior of these features. Of course, we have much better telescopes today, and we have much bigger telescopes, so we can have a closer look of these dark regions called sunspot. And as you see from a ground-based telescope of 1.5 meter from one of the Canary Islands, we see these objects with concentrated magnetic field regions. They are darker than the surroundings because they absorb certain amount of energy, so they are not as bright as the surrounding medium, and so on. How does these sunspots come about? These are magnetic structures. As I said, these are like a magnetic tube. They come underneath the surface, and these we call them magnetic field lines. And these magnetic field lines, when they penetrate the surface, it forms a pairs of sunspots. This is a one polarity, and this is another polarity, and they're connected by these kind of loop structure. And sometimes because of some instability, these loops entangle, and then they break apart. And these, breaking apart of these magnetic structures, they give rise to the solar storm. So as I said, that I am going to talk mostly about the solar storms, which happens on the surface or in the atmosphere of the sun. Now, when these solar storms are happening, here again another movie from another NASA satellite, where you see these regions where there are many sunspots. We call them active region, and after they become unstable, there are lots of material which has been flown into the interplanetary space. Some material falls back, and this allows us to study these plasma material, because solar atmosphere is in a very hot state. It's about the millions of Kelvin temperature. So the state of the matter is in the fourth state of, we call it fourth state of matter, which is the plasma matter. And then you can study atomic physics, particle physics, nuclear physics, you name it. If you are any physics students are there, how solar physics enables our understanding of these branches, I can really discuss for hours. So here today I'm just focusing on these regions, which are called active region, which explodes. They give rise to solar storms, and when the solar storm travel in the interplanetary space, what is the impact they can make? These same solar storm, now I'm showing you movies taken from Parker Solar Probe. This is one of the NASA's really unique new mission, which is really traveling much closer to the sun. And for the first time, we are able to, really see these solar storms almost like in situ, like when the solar storms passes through the satellite. We study the properties of the storms, what kind of matter is there, what kind of charge is there, what kind of magnetic field these solar storms are carrying. So here you can imagine that this is not a very pleasant environment to be. So if you are thinking about a space journey or a voyage through this heliosphere, then you have to encounter the solar storm once in a while, whenever there is a huge explosion happening in the solar atmosphere. So it is important to know when such a solar storm can happen. And as is in our celestial environment also, that the weather forecast is a very important area. So now it has become now a very important thing to understand why the solar storm. So now, of course, theoretically, through simulations, these are all computer, toy, which are generated by a very sophisticated high-performance computing devices. They are able to now reproduce that what is the impact of the solar storm when this arrives and when it impacts with Earth's magnetic field. There are effects which happens in we call it the night side. This is the sun side, and this is the night side of the of the Earth. And if you are traveling within these different trajectories through satellites, you are going to experience all these material. You can see there's a huge CME, we call this coronal mass ejection. These are the manifestations of the solar storm, and when they interact with Earth's magnetic field, what kind of effects it can cause in our neighborhood. So this particular subject area is called the space weather. As I indicated, that we need to know when such a storm happens for a fisherman or a navy personnel. Now the space companies, whoever is using the space, need to understand when such solar storm is likely to happen and what are the impacts. It can impact our satellites directly. The satellite trajectory it can change, because when the satellite goes through the atmosphere, it experiences certain atmospheric drag. And when such a storm is happening, as you saw from the previous simulation also, that entire density was a completely changed. Obviously, the atmospheric drag, the satellite which will be facing, will also change. Of course, it can affect our aeroplanes as well. Some of these planes actually go through the very long route through the polar region, and the polar regions are more susceptible to get these energetic particles which are coming from the sun. They try to enter through the polar region to the earth. That's how you see the beautiful auroras and so on. And you can imagine that if you are flying around those regions, you are getting bombarded by these highly energetic particles which is coming from the sun. So then again, our communication gets affected. So the radio wave disturbance, because we are very much responsible or dependent on the ionospheric condition. All our communications, they get reflected in the ionosphere. So if the ionosphere conditions are changing because of the storm, our communication will get disturbed. We have lots of these kind of electric grid distributions. We have transformers. When such highly energetic particles come, they create induced currents, and those induced currents will directly affect into these grids, and you can have complete blackouts. These are actually happening. It's not all theory anymore. So there have been such many incidences, and now we are getting only aware of the effect of these solar storms. So for all these activities, there are many satellites in space. This is called the Heliophysics Systems Observatory. There is a satellite from NASA. There is a satellite from European Space Agency, from Japanese Space Agency, Russian agency. So you name it. There are many satellites. Some are there within the Earth's magnetosphere. Some are there slightly larger distance. And as I was telling you, these are the most recent ones. The Parker Solar Probe, which is traveling much closer to the sun. Solar Orbiter, again, a very interesting experiment from European Space Agency, which is going out of the ecliptic and trying to see from a different vantage point. So there are n number of such satellites. From India, we've never had anything on our own. So we are actually in a golden age of solar and heliospheric physics now. We could launch our own satellite called Aditya L1. We have traveled to a distance of 1.5 million kilometers away from the Earth and have gone to a very vantage point. We call it Lagrange 1. So Lagrange 1 is a location where we could have a continuous view of the sun. And then also anything coming from the sun, all these particles of radiation, before it reaches Earth, it has to go through Lagrange 1 location. So we have a possibility of remotely looking at the sun and study when such storm can happen, and if the storm happens, where exactly it happens, how it can travel. And then when it reaches the Lagrange 1 point, we can also do properties or characterization of these storm particles, their energies, their magnetic field, and so on. So we call them in situ observation. So it's a combination of a remote sensing payloads and in situ payloads. So this is the first of its kind of an observatory class mission. We have multiple payload. We have several payloads, in fact, 7 payload, 4 remote sensing and 3 in situ observation, which is looking at the sun and the effect of the space weather. There could be many scientific problems which can be tackled by the combination of these multi-wavelength capability. What are the different wavelengths we have? We are looking at, we are seated at L1. We have a solar ultraviolet imaging telescope. This works in a near ultraviolet image. We take full disk images of the sun. We have a coronagraph. What we do is we block the solar disk light, and then only we can see the outer atmosphere, which we call it the corona. Typically, to see the corona, you have to wait for a total solar eclipse, because the coronal emission is 1 millionth time fainter than the disk brightness. So unless you can block perfectly the disk light, you won't be able to see the coronal emission. And typically during the total solar eclipse, the moon perfectly blocks the solar disk. Of course, you have to be lucky to be in the shadow, the perfect shadow of the moon, and travel to that portion of the earth to see this corona. But then artificially, we can block the solar disk light and then also can image and study the corona. That is what we are doing with this visible emission line coronagraph. Then we have two X-ray spectrometer. One is looking at the high energy X-ray and the one is looking at the solar low energy X-ray. As I said, during the solar storms, there are very highly energetic, particles which get generated. To study their properties and the radiation and all that, we have these for in situ, this remote sensing instrument. Additionally, we have three in situ instruments. These are particle detector, one from looking at the electrons, then these are looking at the ions, and the magnetic fields properties can be also studied when this such huge storm passes through the satellite. This is a very, very quick glance. I will show you what all images we are receiving from our coronagraph. So this is our coronagraph images. Beautifully, we are able to see very, very close to the limb. This is the first time we are able to study really the spectroscopic properties of these, emission which is coming from the coronal, low coronal heights. So this was not there with any other satellites. So that's the beauty of, our coronagraph, because whenever we are going to space, we are trying to, design instruments which is going to look at certain regions of the any astronomical object you can name it, which others are not doing it, because we have to have our own uniqueness as well. So this is our unique results which are coming, and you will see many results in the real good journals. This is the solar near ultraviolet imaging telescope. Again, we are able to record slightly lower atmospheric images. These are the regions, again, where there are strong presence of magnetic field. We call it active regions, and we can study their, dynamics and so on. When these active regions are very, very close to the limb, we are able to capture the initial phases of these explosion. What was happening is we had other instruments in the other satellites, but studying the really source region of these huge explosions where and different wavelengths was not there. So we are able to see that in the near UV. We are able to see these huge fluxes changes in the X-rays. And this was a really unique period of 1 week in May 2004. Typically, these X-class flares are the strongest flares. Normally, it doesn't happen very often, but it was a very unique week where we could really see these flares, many such flares in the same week. So this was recorded. So these huge spikes corresponds to excess X-ray energy which is being captured by our remote sensing instrument. We looked at the other high energy spectrograph as well, and we could see the similar kind of spikes. And by studying these properties, how fast these spikes are, what is the decay time, we can study the properties of this storm, its generation mechanisms, how it is evolving with time. Magnetometer, as I said, those happened in the sun, but now after some time you see that when this magnetic cloud or these storm has arrived in the Lagrange location, we see these huge fluctuations in the magnetic field, and that will allow us to tell what is the structure, what is the strength of this, and when it impacts the Earth magnetosphere or any satellite in space, how much impact it can do. So all these calculations are now possible because of these instrument availability. Just very briefly, I will say that there are many missions in the contemporary period, but there were another mission which is very unique of its kind called Prova 3. Why I'm showing this was also launched by our own, ISRO's PSLV launcher, and the idea is very unique. There were two satellites which were clubbed together and sent into the space in a highly elliptical orbit. But when they're really away from the sun, they are actually flying with a formation flying. The idea is that this first satellite, which we call it the occulter satellite, that is creating a shadow of the solar disk light, and the second satellite is observing the corona. So it is like a natural total solar eclipse you create in space. And these two satellites are separated by about 150 meters. So you can imagine that these two satellites are moving with 1,000 km/s kind of speed in space, but they are able to maintain a very very steady 150 meter. You can imagine that if you have to drive two high speed SUV vehicle in a highway, maintaining a precise distance between this, and the separation has to be kept at constant, and also the sidewise movement can be as precise as 10 millimeter. You think about it, these are called technology demonstration mission. The coronagraph spacecraft must remain within this shadow area cast by the occultus spacecraft in order to achieve the desired sun occultation. Otherwise, this solar disk light will be not really forming. So you can imagine here it is showing what kind of accuracies are required, and this is really fantastic. And you see these kind of images are coming. It's very similar to the total solar eclipse. Also, it has a lot of complementarity what we are observing. I showed you that green light image from our coronagraph, which has a spectral property. These do not have a spectral property, but it has a polarization property, which also gives you certain indication about the magnetic field and so on. So how complementary it is for a global science. So what is important is to have this coordinating observing plan with our Aditya mission and other contemporary space mission. I indicated here few. This is the Proba 3 mission, which I indicated here. There is a Punch mission you heard in my introduction. This is a NASA mission. I've been involved with that. Then ESA Solar Orbiter is there. So what is important is that science is beyond boundaries now. So it is so important that, of course, we need consortiums within the country to build the community, to build the instruments and to fly with our own satellite. But then the complementarity is also necessary for collaborating with international community, international space programs. So that's a space era. But I would say that this generation is so fortunate. This is the first time in our union budget it was announced that for a ground-based astronomy, there are 4 major facilities are going to be supported by government. I think in my own life, such golden opportunities was never there. We have been dreaming for this kind of, large ground-based telescopes from our own country. But, the largest we could, achieve was a 50 centimeter telescope for solar observation. Now we are talking about a large solar telescope from this beautiful Merak Island, adjacent to the Merak Lake. Merak is the name of the village. This is the Pangong Lake. And then we are also thinking about almost a 14-meter class, segmented mirror new telescope at our existing observatory at Hanle, where currently we only have a 2-meter telescope. Also, we want to upgrade that 2-meter telescope into a 4-meter plus class telescope as a immediate, step, which is Himalayan Chandra telescope upgrade. And then there is a huge planetarium with a very modern LED, panels and so on, also has been approved by the government. So I think a combination of the space and ground-based astronomy is really into a emerging domain now. So this is my sort of my baby. For last 15 years we have been working for this National Large Solar Telescope project. We have already done some observation. I spent actually 2 winters almost here looking at this sky conditions and the site parameters and so on. We have this design of this telescope now. So hopefully in 5 years' time, we'll have our beautiful own, one of the largest solar telescopes in the world from that side. That's all from my side. Thank you for your attention. As you heard, I was also involved with this, our currently the largest optical telescope, 4-meter from Devasthal in Nainital. And this is the beautiful view of the Himalayas from our observatory site. So we are fortunate that an astronomy allows us to, look at the space, look at the, at the earth, and then have these divine blessings to do our science. So thank you. That's all from my side.
Thank you. Thank you very much, Professor Banerjee, for the fascinating and insightful lecture. I really like the animations and presentation. It was really engaging. And thank you for deepening our understanding to our nearest star, the sun. And now we would like to go for question and answer sessions. So the first question from Soumya Das Gupta, Nicer. Can we say in a star which conditions of a region in the star is responsible for the magnetic field being different there and thus sunspots being formed there? Why only those regions and not others? And second is, can we predict solar storms beforehand and how?
Yeah, very, very good question. So as far as sun is concerned, so it's a, it's a middle age star. So we know what is happening inside the solar interior. So these sunspots, as I said, are magnetic regions. They get formed in the base of the convection zone. So the convection zone is the last 30% of the interior of the solar interior. So when these flux tubes come, so because of the rotation of the sun, and since this convection is there, we have certain models which allows us to sort of predict where these sunspots will come. So I did not talk about it today. These sunspots also undergo activity changes with time. So we call it solar maxima and solar minima. There's an 11-year solar cycle, and the initial period of the solar cycle, the sunspot appears in the higher latitude, and then they move to the lower latitude with the progression of the solar cycle. So we do have a general understanding where there is a likelihood of, these major sunspot active regions will come. For other stars, which are at a sort of a different stages of its evolution, from again models, we can say that where these star spots are likely to happen. So that way we have a reasonable understanding, but again, it is not very, very precise because it's not a very simple linear system. It's a very non-linear stochastic system. So there are variances and so on, but we have a general understanding. The other question, what you said, that is sort of the cradle of everything, that whether we can predict the solar storms. There are lots of effort in that. We have understanding that these regions will give you solar storm, but when exactly that solar storm will happen, that is being always a challenge, because depending on the complexity of these active regions, the time depends. We can observe these active region continuously and see its progression, and through that we are able to now predict, and the predictions are about 80% with the success. But I mean, there are lots of new development happening in this area because of AI, because of machine learning and all that. We are able to feed lots of new data, new models with highly capabilities of the supercomputers. We are making a huge progress. So the prediction is also going to be much better now. As you can see, for our Earth atmospheric models also, the same challenges were there, but now things have improved a lot in recent times, and we expect in solar scenario also we'll be able to achieve that.
Thank you. Thank you very much, sir, for addressing this question. And next question from Rajesh. What type of material used to bear such temperatures near heliosphere, and how the durability of detectors are ensured?
Yeah, very, very good point. I must point out that our own Aditya L1 mission has gone to around Lagrange 1 point. So this is only 1.5 million kilometer, from Earth, but this is only 1% of the distance from between the sun and the Earth. So it is not really that adverse, and the conditions and the temperatures and all that are not so high. But there are other missions like the Parker Solar Probe and Solar Orbiter that has really required a completely new type of material. They had lots of composites. They had a shield in front of the telescope also. So in fact, in the technology, it was a huge challenge and demonstration what kind of composite material you can and how thick that material should be ahead of the telescope to protect these telescopes. Also, I must point out the Parker Solar Probe is not able to look at the sun at all. They are actually looking away from the sun, because if they look at the sun, they will be burnt away. So that way they are looking much away from the sun and trying to capture those solar storms when it comes out into the heliosphere. So Parker Solar Probe is sort of a really a highly material science technology demonstration, you can say. Similarly with Solar Orbiter as well. So these sensors, as you rightly pointed out, needed to be tested in a laboratory in such conditions. So we call it hardening. They are bombarded with a lot of particles, and these sensors are not the same as you will find in the market. Each sensor costs several crores. So these are really, really very, very sophisticated new sensors which are developed only for this purpose, and they're tested as well. And in fact, I was told even from my ISRO colleagues and all that, you buy 100 chips to make such devices, and then after testing, almost 90% is thrown away into the basket. So only 10% gets qualified. We call it space qualification for the final journey. So that way, this is a very, very challenging task of selecting any electronic equipment, sensors for space missions. That's why a space mission typically costs 10 times more than a ground-based facility.
Yeah, selectivity is always challenging. So thank you, sir. So we'll go for our next question. Question from Dr. Bharat Pandey, Government PG College, Ranikhet, Almora, Uttarakhand, India. Sir, since the heliosphere defines the boundary between solar influence and interstellar space, can we think of it as a living shield whose fluctuation not only respond to the sun's activity but also reshape our exposure to cosmic radiation? And could this interplay be hidden driver of planetary evolution and climate?
Yeah, it's again a very, very, very interesting and thought-provoking question. You're right. I mean, we are all in the journey of the cosmos. So how far we can go, this is again will be a question that we go beyond heliosphere. Heliosphere means all the planets, our solar system and beyond. So we have not been able to travel directly to that far. But of course, there are now thought processes going on to use moon as an intermediate step. You travel from here in the moon, you refuel your satellite, your rockets, and then try to go for an interplanetary space journey. So this is still a hypothetical thing that when we will be able to do it. But as you rightly pointed out, that the life or the understanding of things are crucially dependent on this magnetic shield, the heliospheric structure. We are here because Earth has magnetic field. Earth has its magnetosphere. If the planet did not have the magnetosphere, we would not have existed. So, but the same with the problem in the moon also. Moon doesn't have a real internal magnetic field. There's some induced field, but that's not enough to protect us from the solar radiation. So, if we want to think about having some colony or any other travel, we have to think about the interplanetary magnetic field structure and that near that planet environment as well. So, but of course, for our understanding, this is again a journey which we have to do to go beyond and then try to see in situ, what are the properties and so on. So this is our, of course, dream problem, and we would definitely like the coming generation to address this.
Thank you, sir, for answering the question. And we would like to take another question from BAK Bangalore University. How do you explain the 11 years period of sunspot cycles?
Okay. Yeah, this is for me comparatively easier, but I will explain what is the background of this theory. So what happens is the sun, as I indicated, sun rotates about its own axis, but it doesn't rotate uniformly. It will rotate differentially. It's the equatorial regions actually rotate faster than the poles. So and these magnetic flux concentration, which we call magnetic flux tubes, they come from the from the underneath. When they float out, they are sheared. They are getting twisted, because you can imagine that if I am coming out, my head is being rotated at a slightly slower pace, and the tummy is rotated faster. Obviously, there is a shear in my body. So these magnetic tubes, they experience that, and that is one of the reason for their generations, and they come into the surface. But then these flux concentration which are there on the surface, they also die after certain time. And as I indicated, after certain period, you will see that these sunspots are actually coming more closer to the equator. And there are certain smaller field, they go to the poles. And then from the poles, those magnetic fields are getting advected to the base of the interior of the convection zone. So this is a more or less a cyclic thing, and we explain in terms of a dynamo theory. It's very similar to the dynamo in your bicycle. You do your cycling, and because of your motion, you generate the electricity and your light is being grown. So one form of energy is giving rise to another one. So here also in the sun, because of this rotation and convection, we are able to generate the field. And then if you solve that equation, you will see that the periodicity comes as 11 years. As I was mentioning earlier, if there are other stars where you put your different parameters of convection and the magnetic field strength and all that, you will find a different periodicity. So this is directly coming from the dynamo equation, its solution, that the 11-year periodicity is the most dominant period.
Thank you, sir, for answering with very nice analogies. So we'll take next question. Yes. So the question from Rutvik, Aluminous IIT Bhubaneswar. Can you tell more about Lagrange point? Also, do we get solar type storm from other stars?
Yes, thank you. Both are very good question. So Lagrange points actually for a two-body system. If you take a third body in a three-dimensional space, then there are certain stability point. So at Lagrange one, if you put a satellite around its, that particular imaginary point, it's an imaginary point. This is it's like a a fictitious point where their potential has to be minimum. So in that orbit, the force between the satellite and sun balances the force between the satellite and earth, because when you have to make it in orbit, you need always a centripetal force. So the centripetal force is being provided by this force balance, because it is moving. It is not actually stationary at a single point. It is rotating in a big orbit around the Lagrange point, and to rotate that, whatever centripetal force is required, that is being provided by this force balance. The two forces, one is the force between the satellite and the sun, and the force between the satellite and the earth. So this is Lagrange one. There are four other Lagrange points also for a two-body system. So this is again the famous scientist Lagrange, mathematician. In fact, he identified these from the minimum energy consideration and potential calculations on all that for a three-body system. The other question what you asked about the stars, yes, there are CMEs from other stars as well. So as I indicated, the stars need to be magnetically active. So now we know that there are other stars which also gives rise to flares, and in fact sometimes it can give rise to very, very big flare, much stronger than what we have so far observed. In fact, now we speculate if such very, very strong flares which are seen from the other stars, if it happens in our case, then our really our life could be in danger. There could be huge storm, and that will really destroy a lot of stuff. So the answer is yes, there are many other stars which gives rise to stellar storms as well.
Okay, thank you. Thank you very much, sir. So, Professor Banerjee, it is great that we are worried about solar storms, but what about storms on our own planet? Wars, huge disturbance, how to take care of those?
Yeah, I think this is a very important and philosophical question. I'm sure we all understand. Science is there for our better life and peace. This is unfortunate, actually, that we are not able to control all our aggressions, which is unnecessary generating these disturbances. So I empathize with your question, and we are also very much concerned that uh, these are some disturbances which can be avoided. I do not know whether we are responsible for this. To be honest, since you make them ask this question, we are also responsible for our own planet. We are not worried about environmental issues. We go on cutting trees. We are not environment friendly. It is also going to affect us, the next generations. So I think just studying or doing science is not enough. We need to have this understanding what for our advancement is. Science is helping us to take the technology to the next level, but it has to be used for peaceful means only. So that is always a question, whether this nuclear energy generation, alternate sources and all that are favoring the humankind or not. So we need a balance. We need a balance. And so this, how much we can control ourselves and be empathetic with people living in the other side of the globe. This is very important. And I expect that the younger generation, all of us, should voice this requirement. Thank you for asking this question. I think this kind of sense of humanity is very important. It's just not good enough for doing a lot of research or study and no sense for nature or the rest of the world.
Yes, totally agree. I mean, not scientific advancement is not enough. Like even our yesterday speaker also talked about that this is deeply rooted in ourselves, our own mind about the environmental. So thank you. And today's last question I would like to take. What type of radiations do we exactly detect in the experiments, especially in Aditya L1, and what other factors are being measured by the instrument in the satellite to get an overall idea of the research subject?
Okay. So, Shomo, first thing is in terms of the radiation, since as I indicated, the solar atmosphere in a very highly energetic and high temperature, it emits all kinds of radiation from optical, very highly ionized, emissions you can have. You will have X-rays. In fact, in terms of very big flares, you can even have gamma rays. Of course, you have UV light, you have near UV light. So you have the full spectrum of energy which is being radiated out from the sun. So that's why we have these multi-wavelength, instruments. So we have capabilities from Aditya L1 to look at the optical. We have UV, we have X-ray, we have near infrared. We have also infrared, detector on board. So that's why this radiation is fully with the energy spectrum, and also along with that there are particles also. So when such flares do happen, then the particles get accelerated and they travel through the interplanetary space, and before they reach Earth, they will be detected by our in situ particle detectors. So we are able to detect electrons, different ions, helium, alpha particles. All these charge by mass ratio and all that allows also to characterize the properties of these particles, and of course cosmic rays from sun and also other galactic sources.
Yeah. Thank you very much, sir. So thank you for addressing all the questions very nicely and clearly. And it was truly a fitting conclusion of today's session and for our complete Voyage Through Cosmos lecture series. And on the behalf of Bhaktivedanta Institute and all audience, I would sincerely like to extend our gratitude to you for sharing your experience and your thoughts. Thank you very much, sir.
Thank you very much for this opportunity.